Okay, so should I start? Okay, so sorry for the delay. Thank you very much for coming. Yes, we are on topic. So thank you very much for coming. This is my first annual control talk here at the WIP. I have been doing my PhD for almost a year under the supervision of Raúl and Tobias. And today I will talk to you about anticipated synchronization in systems with distributed delay. But first of all, let's talk a little bit just about synchronization. So probably some of you, or maybe even most of you, are somehow familiar with synchronization. But just to give a brief review on synchronization, in a typical synchronization problem, we have two or more systems that are originally doing some movement. And if we plug some kind of interaction between these different systems, we can get them to do exactly the same movement at exactly the same time, as you can see here in these metronomes. So this is a typical example of synchronization. Of course, synchronization can occur in some physical systems, but it can also occur in biological systems. It can occur inside of the brain, or it can occur, for instance, in a very famous case that I guess that maybe some of you will already know, which is the Millennium Bridge. And the day this bridge got inaugurated, a huge crowd went there to see the bridge for a first time, and they start walking. And as I will show you here in one video that probably some of you are already familiar with, they start to synchronize their movement from side to side, and this causes some oscillations in the bridge, and it did lead to the temporal closing of the bridge for some time. So apparently, if you are building a bridge, you also should care about synchronization. As you can see here, the bridge start to oscillate not in a very good way, and they have to take measures. And you can see that more or less the people are kind of synchronized in their movement from left to right. Okay, so how can we model this? Well, there is a simple model that also some of you will be familiar with, which is the Kuramoto model. So in this model, we have a given number of oscillators, which are just simple linear oscillators that each one of them has its own frequency. In principle, we can take this frequency for whatever distribution we want. And of course, if we do not add any coupling at all, each system will do its own movement with its own frequency. But then we can plug in some coupling between the systems. And as we increase the strength of this coupling, we can get all of the systems to synchronize. So here on the other side of the screen, you can see some nice animations. And you can see that here they are using an all-to-all interaction. And when they take a small coupling strength, each system is just doing their own movement. But as they increase the coupling strength, they get most of the systems synchronized in the center plot. And then in the right plot, you can see that all of the systems are fully synchronized. So this was a nice example for a linear systems. But here in this talk, I will be also interested in work with chaotic systems. So let me put a brief introduction to some of the chaotic systems that we will use. So first of all, I will use the Lorentz system, which I believe it doesn't need an introduction. I guess that most of you are familiar with this system. It was a system that was originally introduced to model the Earth's atmosphere, and it has a very nice strange attractor that, as you can see here, and it sort of created a very good hype for this kind of chaotic systems and all of the stuff that came here. And the equations are just, it's a three-dimensional system which has two nonlinearities. And then after this system came out and became very popular, there was a scientist called Rosler, which came up with a different model based on this one, but which was a little bit simpler because it only has one nonlinearity. Originally, it was just a model just a simpler model that was based on the Rosler, but wasn't a model for anything in particular. But it turned out that this model has some applications to equilibrium of chemical reactions. Okay, so these are some of the chaotic systems that we will be using. And now let's go to anticipated synchronization. So anticipated synchronization, of course, is similar to the synchronization that we have already explained. So we have, in this case, two systems that are synchronized, are doing the same movement, but they are not doing the movement at the same time. One system is anticipating, so it's kind of forecasting what the other system will do. So as you can see here, this orange system is going ahead of the blue system. There are several ways in which we can get this sort of anticipated synchronization. Here we will focus on this setup here, which is explained in this diagram over here. So we will create two copies of our system. One we will call it driver, and one we will call it driven system. So the dynamics of the driver system are left unchanged. We do not touch these dynamics. But the dynamics of the copy are a little bit changed. So we couple unidirectionally, which is a difference between the Kuramoto model. We couple unidirectionally the driven to the current state of the driver, but we also couple it to itself, but with some delay. So this is pretty interesting because even though we are not changing dynamics, we are able to forecast the dynamics, even if we are using a chaotic system. So for instance, this animation here is for a Rosler system that we have explained before. So in general, the equations for this kind of anticipated synchronization look something like this. So this over here will be the driver system, and it will be given by an arbitrary function, f, which can be a linear function, but can also be a chaotic or an excitable function, as we will see later on. And here we will have the driven system, which has, again, same function with same parameters, plus some coupling, which is the coupling that we have discussed before. So if we make the assumption that this coupling is 0, and we find what is the solution is this one. So it means that the driven system, the current state of the driven system, is the future state of the driver system. And this was a solution that we got with this assumption, but we can check that if we plug this here into this equation, this is, of course, a valid solution of our system. Then there is the question of whether this solution is stable or not. This, in a chaotic system, is not generally possible to say, but we can work with some approximations. We can work this out in a linear system, and we can also use some simulations and some numerical integration to see whether the solution is stable or not. So this was...
Can you go back?
Yeah, sure.
So you might see this thing when the blue thing comes a bit later than the orange, right? But this would be logical if information goes from the orange thing to the blue thing. But it's not, right? It's not. It's not that the blue thing gets something from the orange. It's the other way around, right? But nonetheless, the orange comes first. So when I first heard about it from Raoul and Vera, I think I was completely confused. Then that cannot be. Right? If you're not confused, you should ask a question.
Okay. No, don't worry. Thanks. Okay, so I mean, this has already been studied. The original paper that originated all of this was in the early 2000s. But then after that, it has been applied to some different systems. So for instance, it has also been applied to spatially extended systems. In this paper over here, they apply it to the complex Ginzburg-Landau equation in just one dimension. And as you can see here, well, this is a complex equation for A and B. And as you see here, they are using the same configuration, as the same setup as I have discussed before, just with a spatially extended system. And you can see here in this plot, in which in this axis you have the space coordinate, and in this axis you have the time. And you can see that indeed this second system, the system B, is able to anticipate what is going to happen in our original system, even for spatially extended systems. And well, this has been studied also in a lot of different setups. I also wanted to mention a couple of slightly different setups that are still very, very interesting, which are these two setups for neuronal models. And for instance, here they have a very similar configuration as I have already explained. They have some model for some group of neurons. But here the main thing is that they are not adding this self-loop that I was explaining before. They are just unidirectionally coupling one system with the other. Here they are using sending and receiver. I am calling them driver and driven, but the idea is still pretty similar. And they showed in this paper that you can, changing the parameters, you can get a regime with delayed synchronization. So this receiver system is going below after the sender, but in other regimes you can find this sort of anticipated synchronization. And also in this same paper they did a very similar model, but they introduced some stochastic input, and they still were able to get some region with delayed synchronization and some region with anticipated synchronization. So these were some nice results that were obtained using anticipated synchronization. Now, let me discuss anticipated synchronization, but with multiple delays, because it's what I want to talk here. So, for instance, what is the motivation of this? Well, the most obvious thing is maybe you have, instead of just having one delay, maybe your system has two delays, or you want to introduce two delays because it can give you some advantage, I don't know. So this will be a first motivation, but also in a more general case, if you have some uncertainty in the delay, so your delay is not exactly tau, but it can vary a little bit, you can also use a distributed delay to model these kind of systems. And last but not least, for example, you can also, in principle, use this to model a delay that changes with time. It's not so obvious, it's not immediately from these results you will do that, but it is a first step toward that direction. So we can, for instance, use a model with just two delays, as you can see here. So we just put two delay lines. But you can also do that with, in general, a generally distributed delay. So you have a distribution of the delays, and then the new coupling term will look something like this, where you have this distribution over here. It is worth mentioning that in the rest of the talk, when I do some numerics, I will just restrict myself to a uniformly distributed delay. So I will just say, okay, the delay has some constant probability to be inside of a given interval, and if it's outside of this interval, the probability is 0. Okay, so this is the setup that I'm going to use. And now let's see some preliminary results for a Rosler system again. So here on top, you have what anticipated synchronization will look like in a Rosler system with just a single delay. So we have already discussed. And as you can see, the two variables are just shifted by some time, which is the delay that we have introduced in our model. But if we now use an uniformly distributed delay, we can appreciate some differences. So what are these differences? Well, first of all, the similarities. Both systems, as you can see, have some anticipated synchronization. So this orange system is still anticipating the behavior of the blue system. But now the trajectories are not exactly the same. So as you can see here, there is some small differences between one system and the other. And these differences, for instance, in the third variable are quite noticeable. Like you have a quite clear amplification of the signal in this third variable. And this is a thing that is pretty interesting for us, because one application that one can think of for anticipated synchronization is to say, okay, I have a system that sometimes it can have spikes, and I don't want them to have these spikes because they are damaging whatever I care about. So I will create this configuration, and when I see that this driven system start to have a spike, I will act on the driver system. Indeed, there are some papers that also work with that kind of things. And of course, in that case, if I have an amplification of the signal, it means that I will be able to catch this spike earlier, and then I will be able to act on it early. So this is an interesting result for us. But this is pretty interesting, but let me move before to a linear system. So let me move to the damped harmonic oscillator. Of course, in this case, this system is very simple, and we are able to analytically solve it. So we know that the trajectory is just an exponential that decays to 0 with a rate minus b times some oscillation. Oops. Okay, sorry about that. And of course, if we know that this is the solution, it does not make a lot of sense to use this anticipated synchronization scheme, because I mean, I don't need to predict what this is gonna do. I already know. But this is very interesting because it is gonna allow us to have some theoretical insights on the problem. And in this linear system, we will be able to work everything out analytically. And I mean, we are also physicists, so we all love the harmonic oscillator, and we work with the harmonic oscillator from time to time. Okay, so I want to do the configuration that we have discussed before. So I will create a second copy of the system, of the damped oscillator, with the exact same parameters that we have discussed before. And now, in general, I will add this coupling that we have discussed before, in which I will plug in a distributed delay. If you are interested in just a single delay, you can say, okay, the distribution is just a delta de Dirac, and a Dirac delta, sorry, and you will recover the result for just a single delay. So how do we deal with this? We are going to do the same assumption as we did before for a single delay. So we're going to assume that these coupling terms are 0. Okay, so this is just an assumption. And if we do some math, we can see that the result is that the driven system is just the driver shifted by a time. So this is a pretty interesting result, because it means that we indeed have anticipated synchronization, and also multiplied by a constant, which is also, yeah.
So just understand this, do you need the coupling with two variables, or could you use the coupling only with a single?
That's a very good question. In principle, you can only put it in one variable and it will still work. Like I am just mentioning, I am just making this assumption in the two variables and putting this to have a more general view. But in principle, most of the works done, they typically say, okay, let's put it this equal to 0 and let's work with that. This is typically what is done. But yeah, you can do both. And typically you will set 1 to 0 for simplicity. Okay, so as I was saying, you have some anticipation time, which is a kind of funny average of your distribution, and you also have some amplification. Of course, if we plug that back into the equations, we can see that since the system is linear, this is still a solution. If the system wasn't linear, then this constant can give some troubles. But for a linear system, this is still a solution. But now the question is this a stable solution, or is it not stable? Or in which region of the parameters this solution is stable? So we can work this out from 2 points of view. We can do it analytically, and we can do it computationally. So in order to do it analytically, we are going to study the stability of this variable over here, which is just the coupling term. So this is the driver system, and this is the integral over the driven. It is worth mentioning that both x and y are damped oscillators. So in principle, if they are synchronized, they are both decaying to 0. So this variable will go to 0 as long as x and y will go to 0. But if the system has the solution that we have already discussed, we hope that this variable will go to 0 faster than the rate at which this variable goes to 0. So using the theory, we can get these lines that you can see there in the plot. And then computationally, we can just launch some simulations. Here, for instance, in this plot, I will just use a system with 2 delays. So here I will fix the difference between the 2 delays. So I will say, okay, the difference between the 2 delays is fixed at 0.2, for instance. And then I will change the average delay, and I will change the coupling strength, and I will compute for each point here, I will compute the trajectory. And then from the trajectories, I can compute the cross-correlation function, and I will plot the maximum of the cross-correlation function. So if the maximum of this cross-correlation function is close to 1, it means that the two systems are similar to each other. And if the maximum of this cross-correlation is not close to 1, it means that the systems are having different behaviors. So doing that, you can see that we got sort of 3 regions here, both from the theory and from the simulation. The first region is this white region, in which the maximum of the cross-correlation is pretty close to 1. And this region is the region with anticipated synchronization. So if we plot a trajectory, you can see that there is, in fact, anticipated synchronization. And from the theory, you can see that these coupling terms are going to 0 faster than the rate at which x is going to 0. Then, as we cross the green line and we get into this second region, oops. Okay, sorry again. So as we cross this line and we get into this second region, we can see that now the frequency in the driven system and also the rate at which this system goes to 0 has changed. And now, of course, there is no longer anticipated synchronization. But however, since both x and y are going to 0, this term over here still approaches 0, but now at a slower rate. And last but not least, we have this region in red, which is not a valid value for the maximum of the cross-correlation function. But the problem here is that the driven system is diverging. So we are not able to compute the cross-correlation function because the driven system just goes to infinity. And as you can see here from the theory, the coupling term also diverges since this y is diverging. So this is pretty nice, but it's kind of confusing to interpret. So another way to, yes, sure.
That if the system itself is down oscillation and then the driver is also down oscillation.
The trick or the problem here is that, maybe let me go back, is that you have also this self-feedback loop. So this self-loop is the thing that injects some energy into the system and is able, but yeah, that's a very good question. I also asked that myself when I start working with this. Okay, so another way to interpret this is in terms of the eigenvalues of the problem. So the eigenvalues of the driver are pretty simple because it's just a two-dimensional linear system. So it only has 2 eigenvalues, which are complex conjugates. Its real part is minus b, and the imaginary part is this omega 0 that we have mentioned before. But in the driven system, since we are introducing this delay into the equations, we can have more eigenvalues. We have the same eigenvalue as before, and then we can have a sum of eigenvalues. But at the end of the day, the only eigenvalue that will matter is the eigenvalue with the greatest real part. So we will sort these eigenvalues by the real part, and we will only care about the greatest of them. So now we will compare this eigenvalue with, let's call it S1, the value with the greatest real part of all the others. And in order to simplify things further, let me say, okay, let me restrict myself to a value of the coupling strength. So I will fix the coupling strength, and I will just vary the average delay and see how these eigenvalues behave. And the evolution is the following. So for the real part, you can see that at the beginning, in this part over here, you have that the eigenvalue which is the same for the driver and the driven, is the dominant one in the driven. And of course, this is what we expect, because if there is anticipated synchronization, they both have to have this, both systems should have the same frequency and behave in the same way. Then at this point, which is exactly on this line, which is this point over here, this second eigenvalue becomes the leading eigenvalue. And with that, you can see that there is also a jump in the frequency of the system. This is what we saw before when we plot the trajectories, that inside of this region, the frequency of the second system was greater. And then as we keep increasing the average delay, we get to this line, which is the moment at which the real part of this eigenvalue becomes positive. So the system starts to diverge. So this was an interpretation of a linear system, but one can ask itself, do we have some advantage by using this distributed delay configuration? So let me do an experiment. Let me take some comparison. So in one part, I will use just a single delay. So the thing that we have already discussed at the beginning of the presentation. And the other part, I will use two delays. I will set the first delay to 0 or to a value close to 0. And the second delay, I will choose it so that this anticipation time is exactly the same as the one here, which is just tau. So we have a fair comparison between the two models. And then if we see whether a trajectory for a given time shift and a given coupling strength is stable or not for this system and for this system. So the region in white, it means that we can get to this time shift with this coupling strength with both of the systems. Then the region in gray, it means that the solution for us with anticipated synchronization for a single delay is unstable, but the solution with two delays is stable. So this is an advantage. So we can get to greater time shifts having two delays.
For the linear.
This is for the linear system, yeah. Then after that, we will discuss non-linear systems. And then, of course, at some point, if we increase the time too much, we arrive to the black area in which both of the solutions will be unstable. So we will not have anticipated synchronization. So this is an advantage of using this for the linear system, of course. But let me just move back to the real world. Let's see what happens with some chaotic systems. So, for instance, here on top, you have again the Rosler system, but now instead of an uniformly distributed delay, I'm just plotting it with two delays. And everything that we have discussed before also applies here. So you can see that there is some anticipation, but the amplitudes in the system, so the height of the peaks, is not exactly the same. And it can also change from time to time, because if you look here, this maximum is below the blue one, but then here the maximum is on top of the blue one. So there is some evolution of the amplitudes that we will study later on. And here you have an example for the Lorentz system also. And again, everything also applies here. So you can see some anticipation and you can see some small variance of the height of the peaks. So it looks like when we are dealing with chaotic systems, the solution looks something similar to what we have before, but now the amplitude is able to change with time. Maybe the time shift is also able to change with time. So we expect to get something like this thing that you can see here in the equation. So how can we study this? I mean, there will be like a lot of different ways and you can sort of try to compute A and tau star, but in order to have a good way to measure it, let us center our results just in the maximum. So we will get the trajectory, compute the maximum of the variables, and then from two consecutive maximum, we can get this time shift, and using the proportion between the two heights, we can get this sort of amplitude. And we will say, okay, this is the amplitude and the time shift at this time, at the time that this peak has occurred. And then we will do that for all the maximum of our system and see how it evolves. So if we do that for the Rosler system with 2 delays, and we use the maximum of the first variable, we obtain these results. So as you can see here, there is some amplification, but the result is not a constant amplification. Sometimes you can get lower values, and sometimes you can get a slightly higher value. So there is some variability in this. And the same happens here for this time shift. It is worth mentioning that for this simulation, the average delay that we are putting is 0.55. So as you can see here, it fluctuates more or less around the average delay. Then if we repeat that for the second variable, we can see that now the variability is even bigger, but it's kind of similar to what we have before. Also now, most of the time, we are not getting an amplification, even though it's possible still for some cases. And with respect to the delay, again, similar results. There is some variation of the delay, of the time shift. And also here, it looks like the average shift is slightly below. And for the third variable, as we have mentioned before, there is a huge amplification. Sometimes there is not that much amplification. Sometimes we get results close to 1, but sometimes we can even get some results close to 4. And there is also, again, some variability for this time shift, as you can see here. And also, the average is slightly above the average delay that we have introduced into our system. And this is kind of complicated, and we cannot explain that from just the linear system that we have said. And it is even more difficult to explain because we can do the same, but using the minima instead of the maxima. And if we do that, we can observe that the behavior is quite different. So for instance, if we do that for the minima of the first variable, we can see that the behavior almost resembles what is happening for the maxima of the second variable, but with some slightly differences. And also the same happens, but the other way around for the second variable. So it resembles a little bit, the minimum of this variable resembles a little bit what it happened with the maxima of the other variable. So in order to sum up these results, let me get to the following plot. So here, what I am doing is a violin plot that maybe some of you are familiar with. So basically, I am saying, okay, let's fix the parameters of our simulation, and let's see how the distribution of the amplitudes is. So for instance, you can see that for the first and the second variable, the distribution of the variable of the amplitude is something like this. So you have some probability that this has some amplification and some probability that is not really amplified. Then this box here is the interquartile range, and this white strip over there is the median. So as you can see here, of course, in the third variable, we have some probability to have a real good amplification of the signal. And then I also did this plot because I wanted to mention that if we now take the two delays to be closer to each other, all the variations are much smaller. And this is an expected result because as we get the delays closer and closer, what we expect is to recover the results for a single delay. So we can say this about the amplitude, and we can also look at the results for the time shift. So again, the time shift for the first and the second variable is just more or less around the average delay that we have introduced here, which is 0.55. But you can see that for the third variable, you have a very clearly bimodal distribution, and also the median is slightly above the average value of the two delays. So this is how the solution looks like, but now we will answer if this solution is stable or not. So in order to do that, we can use again the cross correlation function, And we will plot here the maximum of the cross correlation function. This plot over here is for a single delay, and this plot over here is for two delays separated by a distance 0.6. So it is worth mentioning that now in a chaotic system, we need some minimum coupling strength in order to have anticipated synchronization. Before, the linear system, all of this was in white, but now no. Now we need some minimum coupling strength to have anticipated synchronization. But what we want to do here is to compare these two figures, but it is hard to do with the naked eye just by putting one side by side. So what I will do in order to have a better comparison is to pick a value of the cross correlation function, let's say for instance 0.9, and I will plot the contour line at which this maximum of the cross correlation gets from a value higher than 0.9 to a value smaller than 0.9. So these lines are plotted here. This blue line is for a single delay. So it will be basically this line over here in which the maximum of the cross correlation gets below 0.9. And if we repeat that with two delays separated by some distance, you can get that you can see that if the distance is small, we almost get the same results as before. But if we increase the distance, there are some differences now. And it is also worth mentioning that there are some regions in which the result for a single delay wasn't stable, but now it is stable for a distributed delay. Well, not distributed, just for two delays. So this was all that I want to mention from chaotic system. Now let me mention a little bit about excitable system and we will be done. So as a brief review, what is excitable system? Well, excitable system is basically a system that has one equilibrium, so it has one fixed point, but it has sort of two ways of approaching this fixed point. So for instance, here, if you are in the vicinity of the fixed point, you will just do a small arc of the circumference and get to the fixed point. But if you are here in the other side, you will have to complete almost one full revolution in order to approach this fixed point. Of course, these excitable systems are not so interesting if they are purely deterministic systems, but are more interesting when we introduce some noise. Because if there is some noise, the system will oscillate around the fixed point, but at some point it can cross to the other part and it will do a full revolution, which it will look like a spike in the trajectory. So the trajectory will look something like this, for instance. It will oscillate around the fixed point, and then at some point it will go to the other side and it will complete a full revolution to oscillate again around the around the fixed point again, and then it will do another spike and so on. So now let me analyze an excitable system for single delay and also for an uniformly distributed delay. So I will use the Fishkin-Nagumo system, which is a simple model for a neuron, and has two variables. And I will plug in some noise to this first variable to see what happens. And as you can see here, both for the single delay and for the uniformly distributed delay, we got some synchronization, some anticipated synchronization. And in this case, the results are pretty similar between the single delay and the driven. Indeed, it's even hard to see that there are two different trajectories there. So again, we can compute the amplitude and the time shift for the maxima of the second variable, which is the clean variable, the variable in which we don't have a noise. And of course, now in the single delay case, there is also some variability in the time shift and in the amplitude since we have an stochastic forcing. But you can see that in the case of some uniformly distributed delay, we also got more or less equivalent results for this amplitude and for this time shift. And this was all I want to mention. So just to sum up, we are able to find anticipated synchronization in this system with a distributed delay. And in some of the system, there is also an amplification of the signal, which is kind of interesting for us. So this amplification happens in the linear system, but it can also happen sometimes in a chaotic system, which is interesting. Then we use the damped harmonic oscillator to get an idea of how the solutions of this problem look like, and we were able to compute the exact solution and the stability. And last but not least, we work with some chaotic and some excitable system. We check that there is anticipated synchronization, but that the amplitude and the anticipation time, in this case, are not constant. And the amplitude also can change from time to time. And that's all that I want to mention. So thank you very much for coming. So if you have any question or...
So I wanted to ask about the last part with the excitable systems. If you could go exactly here in the next.
Yeah.
In the previous results that you showed, you showed that when you use uniformly distributed delays or even two delays, then you have more stable, you can reach higher delays which are still stable than when you compare it with a single delay. Here is a little bit more complicated because you have distribution in both of them, but could you still say that in the uniformly distributed delay you can reach high ones? Because from the plots I cannot see, but maybe if you plot the mean value or something like that, you can still say that the one is more stable than the other. You can reach higher delays which are